Welcome to this introduction to digital audio, which will explain the differences between analog and digital audio and how the conversion from one to the other is achieved. This training is required in order to take courses in more advanced technologies, such as Denon's alpha processing. This training will discuss the following topics. We will start by explaining the difference between analog and digital audio. Then we will discuss the advantages of digital audio. Next, we will show how an analog signal is digitized. To reproduce a digital audio signal, we need to make it analog again, so we'll show you how this is done. The training will end with a summary. The easiest way to explain the difference between analog and digital is by looking at a clock. On the left, you see an analog clock. The hands of the clock rotate slowly in a continuous motion, so the clock can indicate every possible instant of time, and nothing gets rounded off. On the right, you see a digital clock. The time is indicated in hours and minutes. Every minute, the value on the clock is increased by 1 minute. The values in between cannot be indicated, unlike with the analog clock. It rounds off the time to minutes. Here we see an important difference between analog and digital. The analog clock can indicate any possible value, while the digital clock rounds off the values to minutes. Of course, the precision of the digital clock can approach the precision of an analog clock by increasing the resolution of the digital clock, by adding an additional value in seconds, for example. Music is fundamentally analog. A music signal starts as an analog sound wave. During a concert, these analog sound waves are picked up by a microphone, which converts them into an analog electrical signal. This electrical signal is amplified and sent to the loudspeakers, which convert it to the analog sound wave that the audience hears. As you can see, the whole signal chain is analog. Unfortunately, we can't always invite a band into our homes in order to listen to music, so we started to record music in a studio. This recording could then be played back at home. Until 1982, consumer audio was stored as an analog signal, on vinyl, for example. Like the analog clock, the music was stored as a continuous signal on the record. This was done with a groove on the record. During playback, the groove is tracked by the stylus that is part of the phono cartridge mounted to the tone arm of the turntable. The stored signal is continuous and can have any value. That's the reason why many people still prefer LPs, because of their high resolution and harmonics. In 1982, the compact disc was introduced, a medium on which music could be stored digitally. The music is stored as bits on the disc, so it contains only zeros and ones. The data on a CD is represented as tiny indentations known as pits. The data is read from the disc using a laser beam aimed at the disc. The reflected light is read by a sensor, resulting in a digital audio signal of zeros and ones. So it is not a continuous signal. Signal values only occur at certain intervals, also known as the sample rate. Also, not every value can be represented. Rounding is required to be able to represent a value with only zeros and ones. So instead of a complete analog signal chain, the signal is converted to a digital signal on the recording side. When the music is played back, it first needs to be converted to analog again. So why would we make it so complicated? What is the advantage of adding these conversions between analog and digital? Well, there are a number of significant advantages to digital audio. The first one is error correction. A CD contains extra information to make error correction possible. So if you scratch a CD, the CD player can correct for this. Another advantage is that a digital audio stream is not very susceptible to distortion from outside. In the event of distortion, the original signal can be recovered easily, which is almost impossible with an analog signal. And finally, a great advantage is the capability of transmitting digital audio. Today, we can download an audio file from the internet with just a single mouse click. Let's now have a look at how an analog music signal is converted to a digital signal. Analog to digital conversion is done in 2 steps. The first step is called sampling. Instead of a continuous audio signal, the time axis is divided into time slots. The audio signal is measured at every single time slot. A CD, for example, has a sampling frequency of 44.1 kHz, which means that the audio signal is measured 44,100 times per second. This results in a sample every 23 microseconds. At each instant in time, the value of the audio signal is determined, so the continuous line is now replaced by dots. A CD contains 44,100 audio samples per second, which was quite a lot in 1982, especially considering that the storage capacity of the CD was limited. However, these days, this level of resolution is rather outdated. So what sampling rate do we need? It all depends on what we want to achieve. Let's go back to the digital clock example. Imagine that such a digital clock would be used to measure times during a professional 100-meter sprint competition. Let's assume that the indicated time shows minutes and seconds. Using such a clock during this contest would be useless, as all participants would most likely finish with the same time of around 10 seconds. The resolution of this digital clock would be too limited for this application. For this application, we would need a digital clock that also measures at least tenths of seconds, like the one you see here. This will result in different times for the participants, so that we can determine who is the winner and who came in second, third, and so on. It is similar if your goal is a high-performance audio system. You would require a higher sampling rate for better performance. For today's more demanding listener, digital audio signals are available with significantly higher sampling frequencies. For example, sampling frequencies of 192 kHz are already employed for high-resolution audio, which contains 192,000 samples per second. So the time axis contains significantly more sampling points. This will result in significantly more audio samples. The time between samples is now only 5 microseconds instead of 23. So using the 100-meter sprint example, this is equivalent to adding 2 extra digits after the decimal for more precision. So the first step of digitizing music is sampling, which is changing the timing from analog to digital. The second step in digitizing is quantizing. This means that the value of each sample is made discrete instead of continuous. You can imagine that instead of using an analog voltage meter, we will now use a digital voltage meter to determine the value of the audio sample. To explain how quantizing works, let's zoom in on a small fragment of an audio signal. We've already applied sampling to this continuous signal by replacing the continuous time axis with a discrete axis. This has resulted in a sample for each instant in time for which sampling is applied, instead of one continuous time signal. By quantizing, the vertical axis containing the value of the audio signal is also made discrete. The values of the audio samples now have to be moved to these discrete levels, which are indicated by the orange lines. Values between those lines are not allowed. The first sample on the left is positioned exactly at such a discrete level, so no problem here. The second sample is located between 2 levels, so it will be moved to the nearest level, which is the level below. The third sample will also be moved to the nearest level, which is the higher level. The fourth sample will stay where it is. The fifth sample will move to the higher level. This is done for all samples, so they can only have a value equal to the quantization levels. Imagine that the indicated levels represent the full audio range. So in total, we quantized audio signals using 8 different levels. To represent this in bits, we need 3 bits because, with 3 bits, we can uniquely identify each level. If we were to use 1 bit more for the quantization, that is, 4 bits instead of 3, this would result in twice as many levels, so 16 levels instead of 8. With 1 bit more, you get a much more precise quantization process. Whenever you apply quantization, you get an error. The difference between the original value and the quantized value is called quantization error. When just a very rough quantization is done, which is the case when you apply a low number of bits, you can actually hear this quantization error as noise. Here is such an example. The maximum quantization error that can be made is equal to half of the quantization level. So, the more bits we use, the lower the quantization noise, and the better the final audio quality. Compact discs employ 16 bits, which gives you 65,536 quantization levels. Imagine the maximum signal value is 1 volt. In that case, the quantization error would be a maximum of 0.00003 volts. There are different ways to digitize an analog audio signal. However, the method described so far is the most popular one. This is called PCM, and it was invented during the development of the compact disc. Denon actually developed this technology way back in 1972 in a professional recorder, 10 years before the CD was introduced. CDs also use the PCM format, using a sample rate of 44.1 kHz and 16 bits per sample. Using these specifications, a CD can store up to 74 minutes of stereo music. When you want to play your digital music back on your hi-fi system, the inverse process will take place, digital to analog conversion. Let's have a look at how that process works. During digital to analog conversion, the discrete time axis is made continuous again. During this process, the samples are connected to each other again, as demonstrated here. So now the time axis is continuous again. The final step is to make the sample value continuous again as well, to get rid of the staircase signal. This is done by applying a low-pass filter. Let's compare this to the original analog signal. As you can see, they look similar, but they are not identical yet. Improvements can be achieved by improving the resolution, for example, by increasing the sample rate and the number of bits. We have now arrived at the end of this training. We started this training showing that music is essentially analog. We showed the reasons why music is digitized, for example, error correction, less susceptibility to distortion, and transmission capabilities. The digitizing process is done in 2 steps. First, the continuous time signal is made discrete by applying sampling. Then quantizing is applied, which allows only certain values for a sample. We saw that the higher the resolution applied to both steps, the better the result for the final analog signal that gets reproduced by your loudspeakers. Thank you for participating in this course. You are now ready for the exam. After that, you will be ready to take other courses that use the information discussed in this training, such as the course about Denon's alpha processing.